All right, so last bit of information that I want to emphasize before we go on to more complicated examples is this. It's obvious because the derivative of a constant is 0 that the antiderivative is ambiguous up to a constant. But it's very important to realize that this is the only ambiguity that there is. So the last thing that I want to tell you about is uniqueness of antiderivatives up to a constant. The theorem is the following. Theorem is if f prime equals g prime, then f equals g, so f of x equals g of x plus a constant. That means not only that these are antiderivatives, all these things with these plus c's are antiderivatives, but these are the only ones, which is very reassuring. And that's a kind of uniqueness, although it's uniqueness up to a constant, it's acceptable to us. Now, the proof of this is very quick, but this is a fundamental fact. The proof is the following. If f prime is equal to g prime, then if you take the difference between the two functions, its derivative, which of course is f prime minus g prime, is equal to 0. Hence, f of x minus g of x is a constant. Now, this is a key fact, very important fact. We deduced it last time from the mean value theorem. It's not a small matter. It's a very, very important thing. It's the basis for calculus. It's the reason why calculus makes sense. If we didn't have the fact that the derivative is 0 implied that the function was constant, we would be done. We would have calculus would be just useless for us. The point is the rate of change is supposed to determine the function up to this starting value. So this conclusion is very important, and we already checked it last time, this conclusion. And now just by algebra, I can rearrange this to say that f of x is equal to g of x plus a constant.